everyone, my name is Ruei-Yang. The title of my research report today is SubspaceNet Neural Network Construction for Direction of Arrival Estimation. I will explore a deep learning solution designed to improve the accuracy of the direction of arrival task. And this is my today presentation's outline. First is my research background. Second part is deep learning-based solutions. Third part is regularization strategies. Fourth part is experimental result. And final part is the conclusion. Our research is motivated by critical safety applications such as the real-time monitoring of wind turbine blades. Direction of arrival or DoA estimation is the key non-invasive technology that allows us to locate the source of abnormal sound or vibrations. But the original deep learning methods face performance bottlenecks. The fundamental text of DoA estimation is the accurate spatial localization of one or more single source. This is achieved by deploying multiple sensor arrays to receive and process incoming signals. Additional approaches to this are called SubspaceNet methods. Their core principle is based on the eigen decomposition of the received signal's covariance matrix. A classical algorithm is music, which works by dividing the observation space into single and noise subspace, and then searching for direction nearly orthogonal to the noise subspace. A more advanced variant is root music, which transfer this search into a polynomial root finding problem for higher efficiency. Although these methods have excellent higher resolution potential under ideal conditions, their performance is limited by strict assumptions in complex real-world applications. However, these traditional methods have the significant flaw. They rely heavily on idealized models. In the real world, when there are inconsistencies in the array's hardware, like gain or phase difference, or when there are sensor position deviations, the model becomes mismatched and the accuracy drops significantly. To address the challenges of traditional methods, we propose SubspaceNet. Its core idea is not to replace classical algorithms but to enhance them in a data-driven approach, using deep neural networks to learn from data how to bridge the gap between reality and ideal models. The flowchart above shows our training process. First, the original signal is converted into an essential covariance matrix and input into the SubspaceNet. The network's task is to learn how to refine this potentially imperfect matrix into an ideal surrogate covariance matrix. During training, we input this surrogate matrix into root music because it is differentiable. Finally, we calculate the loss based on the estimate result and the true angle, and optimize the entered network through backpropagation. The flowchart below shows that the trained SubspaceNet models can generate a surrogate covariance matrix, which can be feasibly combined with any traditional subspace algorithm to enhance its performance in complex scenarios. The first step in the SubspaceNet training process is data input and feature instruction. The process begins with the raw input, which is the observation single snapshot matrix from the antenna's array. As the equation clarifies, each single snapshot value is a vector. Each element of that vector is a complex number in the from A plus bi, which represented the amplitude and phase information captured by each antenna element. The figure on the right shows the physical step-out begins considered. The uniform linear array ULA consists of n antenna elements with a uniform spacing d between them. This array receives a single sk arriving from a direction represented by the angle theta. From this original single, we perform the main feature extraction step. We calculate the empirical covariance matrix using the equation. The concrete matrix is then structured into a specific complex tensor format and serves as the final input feed into the SubspaceNet DNN. After we extract the feature tensor, it feeds into the core of our models, the SubspaceNet DNN. The architecture is composed of two main parts, an encoder and a decoder. The encoder takes the input tensor and processes it through three CNN layers. A key feature here is that we use small 2x2 covariance convolutional kernels, as visually demonstrated by the example on the right. This operations allows the network to efficiently capture local correlations in the single data. The overall purpose of the encoders is to compress the input and extract the most meaningful features. The decoder process then takes these compressed representations and use the convolution layers to reconstruct the data with the goal of producing the clear surrogate covariance matrix. The ARILU activity function used in the SubspaceNet model, unlike standard ReLU, which discards negative values, ARILU can retain both positive and negative values into in a single, which is crucial for processing sensors data. ARILU achieves this by dividing the input into positive and negative components, and then combining them, thereby simultaneously preserving both the positive and negative information in the single. The structure doubles the number of feature channels in the ARILU layers. The final stage of the SubspaceNet models is post-processing, which aims to convert the raw output of the neural network into a valid covariance matrix that can be used by the root music algorithm. This process first reshuffles the network output into a n by n complex matrix, and then calculates its simple covariance to ensure that it is positive definite definite matrix. The root music algorithm then uses this matrix to construct a polynomial and solve its root, and finally estimate the DoA angles of the singles based on the root that is close to the unit circle. In the design of a loss function, we mainly address two challenges. The first is the order problem that produces huge errors, and the third is the periodicity problem that is very close in actual angles. For this reason, we designed this root mean square periodic error RNSPE loss function. We use the minimum operation to traverse all possible permutations and combinations to find the best pairing of the predicted value and the true value. Then, for each pair of angle, we use a periodic errors function E to calculate their actual difference. The final errors values obtained in this way becomes a reliable base for us to update the model parameters. To solve the problem of the overfitting of deep neural networks due to small amount of data, we used L2 regularizations, which penalize large weight value to make the model smaller and more generalizable, thereby learning the true terms rather than noise. We propose the first regularization strategy. We named their specific L2 regularization. This method only regularize the hiding layer, which is the main source of overfitting, without affecting the input and output layer, since the model complexity is concentrated in the hidden layer. Regularizing it can directly suppress overfitting. At the same time, we retain the flexibilities of the output layer to ensure that the model's test performance is not affected. This target approach can effectively prevent overfitting and maximize model performance. Next, we propose a second regularization strategy, which named dynamic L2 regularizations, which regularization strength lambda is dynamically adjusted during the training process. In the early stage of training, we use a very small lambda to give the models maximum freedom to quickly learn the main features of the data. In the later stage of training, when the model may start to learn noise, we increase lambda and impose stronger concentrate to effectively prevent overfitting and ensures that model focus on learning the real data patterns. And final is my experimental result. In the experimental result of SubspaceNet, we compare the performance difference between traditional methods and methods enhanced by SubspaceNet. First, it should be noted that the final DoA estimations errors unit in the chart are angled, so lower values indicate better performance. In the figures, the baseline error of traditional music is around 9.9 degrees. After being enhanced by SubspaceNet, the errors decreased to 4.95 degrees, representing an improvement of nearly 50%. In the root music sections, the effect of root music is even more significant. The errors of the traditional methods reach as higher as 22.3 degrees, but when combining with SubspaceNet, the error dropped to 1.50 degrees, represented a 90% improvement in performance. This result clearly demonstrates that whether it is music or root music, SubspaceNet can serve as a powerful front-end model, significantly enhance the accuracy of existing subspace algorithms. In the regularization strategy experimental result, we compared 4 strategies amongst which the key indicators is the validation loss, represented the generalization ability. The results shows that overfitting is the most serious when there is no regularization, where the traditional scoreboard regularization has improved, but the effect is limited. The dynamic and lower specific strategies we propose performance significantly better. Amongst them, the strategy that only regularize the hiding layer achieve the lowest and most stable validation loss. Proving that it has the best effect is surprising overfitting. In the experimental result table, our proposed hiding layer regularizations REGH achieve the lost validation loss with the average error of about 0.3 degrees and a performance gain of more than 73%, which is the best performance among all strategies. At the same time, the strategy that only regularize the output layer perform the worst, even worse than not using any regularization. This strongly proof keep the output layer flexible is crucial. In conclusion, our research successfully proposed the SubspaceNet framework, and its cross is used deep learning to create an ideal surrogate covariance matrix. This allows traditional DoA algorithms to overcome difficult challenges. Furthermore, our proposed layer-specific and dynamic regularization strategy will prove to effectively suppress overfitting and significantly enhance the model's generalization ability. For future work, we plan to introduce complex neural network, hoping to more efficiently process the phase information within the single and further improve model performance. Thank you for your listening.